Hello and welcome back to Graph Theory. Been missing you guys, so I thought I'd start this video lecture with our old class picture. I'm working on getting a downsized version of this on the Canvas page so you guys can nostalgically remember the good old days as well. But let's get down to work here. The second video lecture, still talking about distance in graphs, still coming from section 4.1 in the book. And in this video, I've got three goals. I want to tell you what two specific kinds of paths in a graph are called, or are radial and diametral paths, or diametral paths. I want to talk about the properties of the distance function, and in particular, tell you that they comprise a mathematical object called a metric. A distance measuring function is called a metric. It has certain properties that we want to look at. And then I want to, well, have you conjecture a couple of results actually by looking at a specific example, and then try to state and prove those conjectures, and that'll be at the end. All right, so you've seen the first video. We've introduced distance. I listed some terms there that if you need to, maybe you'd rewatch that thing, or these things I'm assuming are fresh in the mind of the person watching this, eccentricity, diameter, and so on. Okay, so I like to make the definitions with an example in front of me, so let's do it. Here I've drawn a graph, a connected graph, and before I started the video, I went ahead and calculated the eccentricities of each vertex, and I wrote that eccentricity in red right next to the vertex. So it's a good chance for you to maybe stop the video and check those calculations. Make sure I didn't make any mistakes, and make sure you know what I mean by the eccentricity of a vertex. But let's, this is kind of just a little vocabulary review. You remember that the radius of a graph is the minimal eccentricity. It always exists because you have a finite set of integers. You can always choose the smallest one. Looking around at this graph, it looks like its radius is 3. Smallest eccentricity I see on that graph is a 3. Likewise, the diameter is the biggest eccentricity. So looking around at each of the eccentricities, the biggest diameter I see is 6. Or sorry, biggest eccentricity I see is 6, so that's the diameter. The center of a graph is, well, by definition, it's the set of vertices whose eccentricity is the radius. So we're looking for all the vertices with eccentricity 3 in this picture, and it looks like there's just one of them. The center of this graph has a single node in it, and that node is B. The periphery of a graph is the set of vertices whose eccentricities equal the diameter. So there are 2 vertices in that graph whose eccentricity is 6, the diameter. They are E and J, and so the periphery has 2 points in it as well. All right, so that's just kind of a recap. So let's define a couple of new terms here. I've got kind of a mini version of that graph here, so let me just pull it to the top of the screen. So paths from any central vertex to one of its eccentric vertices, that is a vertex that is as far away as possible from it, its distance would be the radius. It's called a radial path. Our example has 2 of them. There's 2 radial paths. They're drawn in blue there. They both emanate from the center. The central vertex, we said, is the vertex B. And then, well, to find a radial path, you have to take a path from that center point that is to a vertex that is the radius distance away from it. And there are 2 vertices in this graph that are 3 edges away from B, and they are E and J. And those 2 blue paths that you see there are the 2 radial paths. All right. A related notion is a diametral path. What do I mean by a diametral path? Well, I mean it's a path between 2 peripheral vertices. In our little example that we're looking at here, there's exactly 1 diametral path in that graph, and it's the path that connects the diametral, or the periphery vertices E and J. And those vertices, they're mutually eccentric to each other, so we call them antipodes. So that diametral path is connecting the 2 antipodes. Okay. So there's a couple of just technical terms for certain kinds of paths in graphs. Let's note here that by the definition of these things, that the length of any radial path is going to be the radius, and the length of any diametral path is the diameter. That's what makes them what they are. Okay. So now some fun. Let's make some conjectures. You probably already have looking at these things, and you can make many more conjectures than what I've listed here. But just glancing at this copy, I erased the radial paths and kept the diametral one. Well, what can you see? The first conjecture I'm guessing at here is that it looks like the eccentricities of adjacent vertices differ by not exactly one, but at most one. Yeah, you pick two vertices that are adjacent, those two that I just highlighted in yellow, B and C. Their eccentricities differ by one. E, C, and D eccentricities differ by one, but not always. Yeah, here F and G are adjacent vertices. They have the same eccentricity. But you can't find a pair of adjacent vertices whose eccentricities differ by more than two in that graph. So maybe that's always true. A second conjecture is that in this graph, and this is kind of going out on a limb conjecturing it from one graph, but it appears that the periphery, it has pairs of elements in it. The periphery kind of comes in these mutually eccentric vertices. Again, this graph is a little bit of a stretch to make that conjecture because it only has one pair of eccentric vertices. But in general, we'll see if we can't try to prove that. Okay. The proof is going to use a little bit of a technical property of a distance function. So let me, I'm not going to prove this property right now. I'm actually kind of hoping you will. I mean, there's three properties really, and I'm hoping you'll prove all three. So this distance function, it's the number of edges on the shortest path between two vertices. It has some useful properties. Let me just let for shorthand here, I'll denote by V, the vertex side of the graph, so I don't have to write so much. So what are those properties? Well, the first one here is saying that the distance between any two vertices is greater than or equal to 0. That's obvious from the definition. It's the length of a path. It would only be 0 if U and V were equal, and otherwise it's some positive number of edges, right? It's a length. The second property is kind of a symmetry property, we would call in abstract mathematics, that the distance between U and V is the same as the distance between V and U. Again, that's obvious. The length of the shortest path between U and V, well, it's the same path between V and U, and they have the same length. The second one, or the third one, pardon me, the triangle inequality. This one is the one I want you to kind of think about an argument. It's doable. It's doable. If you want a little hint, given the vertices U and V and W, kind of consider whether W is on the shortest path between U and V or not. That's kind of the argument that I would try to put together, but I'm not going to say anything more about it right now. That last property, it's called the triangle inequality, and it says something very familiar. If you're thinking about distance in the Euclidean plane, for example, this property is not alarming or surprising at all. It says that the distance between 2 points is never any more than the sum of the distance between that first point and the third and the second. Or if you draw a picture in the plane and think about usual distance, this fact just says that the sum of any two sides of a triangle is always at least as big as the third side. That's why it's called the triangle inequality. In everyday English, this fact is usually pronounced something along the lines of the shortest distance between 2 points is a straight line. You deviate off the straight line from U to V, and you're going to increase the distance. But anyway, so there's these three properties. Any distance function, maybe you've had some other mathematics courses where you've studied this, any function on a set that has these three properties, it's called a metric on the set. And it, in a very natural way, kind of acts like an abstract distance function. Okay, so I'm going to use that triangle inequality in a little bit here, so that's why we're mentioning them. Okay, so let's turn some of our conjectures into propositions here. I think the first one is actually the second fact that I conjectured. So let's see if we can't take a look at the statement of it, and then I've sketched out a proof. I'll try to walk you through it. So the proposition is for a connected graph with at least order 2. Its order is strictly bigger than 1. And then there always are a pair of mutually eccentric vertices, right? So just like we saw in our example, let me just bring it back here. This E and this J, they're vertices whose eccentricities are equal to the diameter, and they're both that distance away from each other. So the proposition that I'm trying to prove to you guys says that any connected graph would always have such a pair of vertices. Cool. Okay. So let's try to walk through the proof. We got ourselves a connected graph. I'm not going to write it down here in the body of the proof. Its order is at least 1. That's strictly bigger than 1. I'm not writing it down. And then well, how do we start? Well, first of all, let me remark that it's never possible that the periphery of a connected graph is empty. Again, because every vertex has an eccentricity and there's got to be a biggest one. So every connected graph has a periphery. And if you pick any point in that periphery, say U, then by definition, there has to be some other vertex in the graph whose distance from U to V, well, it's eccentric to it, so that distance is the eccentricity of U, but in particular, if U is in the periphery, then that eccentricity is the diameter. So there has to be a vertex that's the diameter away, okay? And then because of that, the eccentricity of that vertex V has to be at least that of U. I mean, the way you want to think about this is, well, okay, V is eccentric to U, so it's sort of as far away from U as possible. There might be vertices that are further away from V than U is, and that's all I'm saying here, is that the eccentricity of V is at least that of U. However, U's eccentricity was big. It was the diameter. The diameter is bigger than the eccentricity of any vertex, in particular of V. And we just said that V is at least U, but the eccentricity of U is the diameter. So if you've had maybe some analysis courses or a calculus course, whenever you get a string of inequalities like this, you guys know what I'm looking at when I'm talking about my string of inequalities. I'm looking at these things right there. And the quantities on the extreme ends are actually equal. In this case, it's the diameter of G. Well, then every quantity in that string is equal. Yeah. So in particular, the eccentricity of V is the eccentricity of U. So V is also in the periphery. Its eccentricity is as big as possible. All right. So there you go. U and V are your mutually eccentric vertices, and that's our proof. Cool. Okay. So one conjecture down. Maybe we can mention as a quick corollary to it that a connected graph of order n will always have a diametral path, because you can just take, it's a connected graph, so you take two mutually eccentric vertices, well, they have to have a path between them, and that path is diametral by definition. Great. All right, good to know. There's no such thing as a connected graph without a diametral path. In the next lecture, the last part of this section 4.1, we're going to kind of specialize off to trees, and I want to prove something kind of special about diametral paths in trees, but leave that as a cliffhanger so that you keep clicking. Okay, so what about this other conjecture? We said that looking at that graph up there, two adjacent vertices either had the same eccentricity or they differed by 1. So that's what I'm writing in this theorem. If you have a connected graph, you take any two vertices in its vertex set that are adjacent, so the UV is an edge in the graph, then the eccentricity of U and V would never be more than 1 away from each other. So I'm just writing that down mathematically by saying the absolute value of their difference is less than or equal to 1. Because I don't know which one's bigger, and frankly, I don't care. So I just take their difference and take the absolute value, and I say that that's never more than 1. That's the theorem statement. So let's try to prove it. Okay, so let's pick a couple of vertices in our graph, call them U and V. Suppose that they're adjacent to each other, so UV is an edge. And then again, by the definition of eccentricity, if you pick any vertex in the graph, G, the distance from it, from U to it rather, couldn't be any more than the eccentricity of U. The eccentricity of U is the largest distance away from U. All right, so that's true for any vertex W. So in particular, if we picked a vertex that was eccentric to V, our other vertex, we picked this vertex W to be eccentric to V, then it's also true that the distance from U to that W is no more than the eccentricity of U. All right, so let's look at a calculation. The eccentricity of V, well, it's equal to the distance from V to W because W is eccentric to V. But now I'm going to break out that triangle inequality. The distance from V to W cannot be any more than the distance from V to U and plus the distance from U to W. The triangle inequality says that. The distance from V to U is 1 because U and V are adjacent. Okay, so I'm just replacing that with a 1. And the distance from U to W, we said right up here, is no more than the eccentricity of U. So I'm not really doing anything to that 1, but I'm just replacing. If it's easier, I can kind of underline. This term that I'm underlining in red right now is no more than this eccentricity of U, and that's what justifies that inequality. All right? So now just do a little bit of algebra. We've proven that E of V, excuse me, is less than or equal to 1 plus E of U. Well, that would precisely mean that E of V minus E of U is less than 1 in that order. All right? But this argument was totally symmetric in U and V. I could go back and instead of starting by saying something about every vertex and U, I could make that a V. I could pick W to be eccentric to U everywhere. It's a good exercise for you, actually. Go through the argument I just gave, interchange the roles of U and V, and you'll prove exactly the opposite difference is less than or equal to 1. So we can prove them both. Well, if both of those differences are less than or equal to 1, then by definition, the absolute value of the difference is less than or equal to 1. All right? So that's kind of a way to show that that phenomenon we observed in the graph above, that neighboring vertices, eccentricities are never more than 1 away, is always true in a connected graph. Cool. We'll look at this fact and the next time when we specialize off to trees. Maybe if you haven't already read it, maybe you can kind of wonder, like, what do you think is true in a tree, maybe? Maybe just to give you a teeny hint, notice back here in our example, the only places where you can find adjacent vertices where the eccentricities don't differ by exactly 1 are vertices that lie on this cycle. Yeah. So there's a little hint for you about what might be true in trees. Cool. Okay, let me just find the end here. Oh, I was going to remind you, or tell you rather, that in your homework, you're going to be asked to prove something about this stuff. So I hope these definitions of radius and diameter and so on. But this is kind of a pleasant result. You're going to ask to be showing a proof of theorem 4.2 in the first homework assignment you'll submit to me in our virtual world. That homework assignment, the if probably has an F, so I'll put it in there. If G is a connected graph, then the radius of G is less than or equal to the diameter of G. I would hope that was true. But in particular, the diameter is never any more than 2 times the radius. That has kind of a nice geometric sound to it. Okay, so well, that'll be it for this second video. I hope it's not too long. This is kind of the time frame I'm shooting for so that you can just sort of stay focused on a certain idea. Next time, like I alluded to, we're going to take a look at some of these notions about radius, center, diametral paths, all specialized into trees. So I hope I'll see you there.